Hello everyone, I hope everyone is well. Welcome back to our YouTube channel. I believe this is our second video, and I hope everything is still going well. And please support our channel, like and subscribe to our YouTube channel. And we are really appreciate your support. Today we are gonna revisit U substitution because of the video's audio was not perfect, when we hope this one will be perfect. So we will look at U substitution, which is an integration technique. We will look at integration by substitution. What is U substitution? So U substitution is an integration technique used to simplify complicated integrals by replacing part of the expression with the new variable, normally U. In mathematics, the variable that you use doesn't really matter, but from the name U substitution, we prefer to use the variable U. So it reverses chain rule. This is a fun fact to know about U substitution in differentiation. This is the reverse of chain rule in differentiation. As you can remember that chain rule said you have to differentiate the outermost function first, keeping the inner function as it is. Then you have to multiply by the derivative of the outermost function. So integrating here on both sides, the integral and this will cancel. So you will have this will equals to the integral of f prime at g at x, g prime at x dx. Then this will be the integral. If you make u to be g at x, yes, if you make u to be g at x, so that g prime and dx falls away, this will have the integral, the integral at the function u du, where u is equals to g at x. So let's look at a few examples on this. But the first question we want to ask ourselves is, when do we use u substitution? And we use u substitution when there is a function inside of another function. I remember we said this in the previous video. And the derivative of the inside function is also present. This is important. Or it differs by what? By a constant. These are few examples that we have. This will be number 1, number 2, number 3, and number 4. So for this video, not to be long, I would like to do number 1, number 4, and maybe number 3, I guess. So you will have number 2 to be your own exercise to do after the video. So number 1 is the integral of x squared plus 1, all raised to the power of 8, multiplied by 2x dx. So you have the integral of x squared plus 1 raised to the power of 8 multiplied by 2x dx. So we said when you have the inside function, you make it u. So let u to be equals to what? U to be equals to x squared plus 1, so that du can equals to 2x dx, of which, luckily enough, this is what we have here. So you have 2x dx. So this will be the integral. The inside function is u. So this will be x. Sorry. And this will be just u. And then this whole expression 2x, the x will be what? Will be du. So don't forget the power of 8. So this integral will equals to u to the power of 9 divided by 9 plus the constant c, using the power rule of integration. So this will be just x squared plus 1 all raised to the power of 9 divided by the power of 9 plus c. Yeah, so we saw that we let u be the inside function, and then the u became this expression here. And then, yeah, the integral is simplified to just being an integral of x to the power of 8. So nice things happen from there. We use the power rule of integration to find u to raise to the power of 9 divided by 9 plus the constant c. So this will be x squared plus 1 raised to the power of 9 divided by 9 plus the constant of integration. So yeah, so let's look at another example that we said we want to look at. So we said we want to look at example number 3. So what is the example? Cos 3x times 3. Okay. This will be the integral of cos of 3x times 3 dx. So here we said let du be equals to 3x, so that du will equals to 3 dx, so which is what we have here. So you already have the integral of cos of u, né? The integral of cos of u du. So here we know that this is going to equals to minus sine of u plus the constant c. So minus 3. Sorry, where is the 3 coming from now? Minus sine of 3x plus the constant of integration. So I believe that will be the final answer. So the reason why we are going back to the original variable is because the integral that we were given was with the variable x. So after using the substitution to simplify the integration, so we have to go back to the original variable x. So the last example that we want to look at, it's what? 2x, and then yeah. So we want to look at the integral of 2x over x squared plus 9 dx. So we have to simplify this further and say, okay, we have let du equals to what? X squared plus 9. So du will equals to 2x dx, which is what we have here. So yeah, the integral of what? 1 over u du. So this, because what you have in the numerator is the derivative of the denominator, so this will just be equals to ln absolute of u plus the constant of integration, but this is ln absolute of x squared plus 9 plus the constant of integration. I believe it still is so far. You just have to identify the variable, the function, and then you have to see that this is just the derivative of the function. And yeah, so let's look at integration by parts. Oh, before we look at integration by parts, the summary of u substitution. We say u substitution simplifies the integrals by replacing a complicated inner function with the new variable u. This is what we saw. It works best when the derivative of the chosen inner function is also present. This is important in the integral. So key steps to remember: you have to choose the inner function to be u. In the case that we had, it was g at x. So they differentiate, and then from differentiating u, you will have du, and then here you will have g prime dx by implicit differentiation. Then you rewrite the entire integral in terms of u, and then integrate with respect to u, and then substitute back the original function or change the limit of integration if it's a definite integral. So yeah, we want to look at integration by parts. So integration by parts. So what is integration by parts now? So integration by parts is an integration technique used to integrate the product. This is key, the product of two functions, and what it is based on the product rule of differentiation. So recall that the product rule of differentiation, let's say you have u, v, and then this, so that when you integrate both sides, you will have this as the formula of integration by parts. So this is the formula for integrating by parts. So the integral of u dv will equals to uv minus the integral of v du. Yeah, so when should you use the integration by parts? So you use the integration by parts when integral contains a polynomial times an exponential function, a polynomial times a trigonometric function, a polynomial times a logarithmic function, a polynomial times the inverse trigonometric function. Even, I believe, when you have a trigonometric function times a logarithmic function, for an instance, an inverse trig times a trigonometric or whatever. Yeah, we just use integration by parts when we have the product of two functions that don't have the relationship. Like when you have two functions that you have to integrate, like this one, when they don't have when they are different, when you differentiate them, you don't have a relationship with the function that is being multiplied with, then you use integration by parts. So these are a few examples that we want to do. So, and okay, maybe we'll explain that later when you do the summary of this. Let's do this example, x e to the x, okay? So here, let's say you have the integral of x e to the x dx. Here, you cannot use u substitution to simplify the integral, but rather you will have to use the integration by parts by letting u be equals to. Then how do we choose u? U and dv. Now we have to know how do we choose these two. We have a little trick called Lie8. So yeah, we choose u going this direction. This is the direction we choose u. So here stands for logarithmic function, inverse trigonometric, algebraic, trigonometric, and exponential. So when you see the first one to see here is one that becomes your, let's see in this case is what? It's algebraic. This is algebraic. A comes before E. So this is algebraic. So this will be your X, and then dV will be your exponential e to the x dx. And then what will be du in this case will just be dx, and then what will be your u in your v in this case will just be e to the x. Don't worry about c, because this one you have to integrate, but don't worry about c. So the answer to this, as we have said, the integral of x e to the x dx is equals to what? uv in this case is x e to the x minus the integral of e to the x dx. So we see that this simplifies, this becomes, you have to integrate this as well as just e to the x plus c, and then you can simplify this, take out the common factor e to the x, and then you will have x minus 1 plus c. Yeah, I believe this will be our final answer for this integral. Now let's get another example that we want to look at. Let's look at this one, x times ln of x. So we have the integral of x ln x dx. So this will be u will equals to, according to Lie8, in logarithmic function comes first before algebraic. So we know that ln x will be u, and then dv will equals to x dx. So now du will be equals to 1 over x dx, and then v will just be x squared over 2 when you integrate this. Yeah. So from there, you will have to say what now? You have the integral of x ln x dx will just be equals to this expression times this. So we'll just have, which way is best? Okay. We'll just have x squared over 2 times ln x minus the integral of this times this. So the x will cancel one x in the denominator. So you will have x over 2 dx. So the final answer will be x squared over 2 ln x minus, when you integrate this, we'll have minus 1 over 4 x squared plus c. Yeah, this is the final answer. You can take out x squared as common factor, but yeah, x squared is fine, but no need. It won't look nice or anything. It's just fine even if you leave your answer here. Let's look at another example that we want to look at. Okay, this one's a two body. These two guys will be your exercises, I believe. And then let's look at this one. X times a tan of x dx. So you have the integral of x times tan inverse of x dx. So now you have to use u to equals to tan inverse of x, and then v to be equals to x dx. By now, because I have done so many of these problems, and Lie8 has become part of me. So yeah, but if you still need help of Lie8, you can utilize it. It's a very good thing. Differentiate this. This is v1 over x squared plus 1, I believe, dx. And then this will be what? This will be dv here, dv, and then v will just be x squared over 2. So now when you integrate the answer to this integral x tan inverse of x dx will just be equals to this times this. So x squared over 2 times tan inverse of x minus the integral of this times this. No? So it's going to be x squared. So we can take this half outside of the integral, and then over what? X squared plus 1 dx, ne? I believe. Yeah, so because this also, what do we need here? We need another way of integrating this will be by, we need, let's see, x squared plus 1 over x squared. I think we need partial fraction decomposition here. And we have not covered this in our series. So do we solve it? Because the degree in the numerator is equals to the degree of this. This will require long division first. Oh yeah, for this one, let's hold it here. We'll do this problem when we show the relationship, the problems that contain another different types of integration technique. Because in this video, we just wanted to show you the basics of integration by parts, as you have seen in these two examples. So let's do another last example, maybe on integration by parts that won't require another type of integral, unless if it's u substitution, because we have covered u substitution. I don't believe it will be a problem with u substitution. So let's use sine x, this one. So this is the integral of x sine x dx. So u will equals to x, and then dv will equals to what? Sine x dx. And then this du will be equals to dx, and then v will just be equals to, when you integrate sine, is just cos x. Sorry, you don't have to worry about the constant of integration. So now we will just say the integral answer to the sine x dx will equals to this times this is going to be x cos x minus the integral of cos x dx. So that x cos x minus, when you minus this, is going to be bring a plus, because this has to bring a minus sine x plus the constant of integration. So yeah, that will be your final answer. So this technique is really easy when you have done so much problems to it. This problem, we'll do it later in the series when we have introduced you guys to partial fraction decomposition, because it's another type of integration technique. Yeah. So otherwise, we'll do the summary for integration by parts. So integration by parts is based on the product rule. And then you need the product of two functions. And then the formula, you choose u using the Lie rule. And then we have already stated in the video what Lie stands for. And then key steps using Lie, you choose choosing u using Lie. And then the remaining factor becomes the v, as we have seen. Then compute u, du, and v by integrating the v, and then by differentiating u, and then apply the formula, simplify the integration, the integral, and then rule of thumb. If the integrand is the product of two functions and u substitution does not simplify it, then integral by parts is the correct technique to use. So yeah, guys, I believe and I hope you had fun with this one, and I believe you gained something. Don't forget to support our channel by liking and subscribing. Until the next one, remember, when you like and subscribe, you encourage us to release more content like this. So thank you, guys. Enjoy the rest of your day.